So first we're trying to learn how to figure out how to measure the length of a curve in a space. So in a space, given curve, right? So given curve, right? And you can parameterize it, right? And so T is between A and B, right? So how can I use this, we call the position vector, well, to calculate the length of the curve. Okay. The idea is pretty simple. It's called calculus idea. So we participate partition the interval, right? Bunch of the points, right? Then we get a bunch of the points on the curve. So this will be gamma T1, maybe for example, this is gamma T2, and so on. So my understanding is the length of this curve, okay, we call it the length of the curve, right? The length of the curve C, which is the orbit of that moving object, and described by that formula, gamma of T. This can be almost equal to, right, so use a strict line to measure it. And line segments join the 2 points. So the distance between two points is given by this length, the difference of two vectors, right? So think about that, right? You have two vectors. One is gamma Ti minus 1, other one is gamma Ti. How to measure the distance between those 2 points? You take the difference of those two vectors. That gives the length, that gives the direction of the vector from one point to, yeah, right? So you get this vector. The difference of these two vectors is this vector, and this vector. And then you take the length, find the length, and then this one by, so I'm going to also let delta Ti to be Ti minus 1, the difference of these two. So what I'm going to do is I'm rewriting it. I'm trying to derive the formula using calculus, okay? This is always the idea, partition. Delta Ti, then you put a delta Ti here. So what is inside? This can be replaced by the mean value theorem, another approximation. Okay, it's going to be gamma prime Ti star. Okay, so this Ti star, some points in the interval Ti minus 1 to Ti. Right? Yeah, this is called the mean variance. I think it's called the mean variance theorem. Yeah. So given the difference of the function to the values at two endpoints divided by the size of intervals, that's going to be it is going to be the derivative at some point. Then if you pass to the limit, all the delta Ti approaches 0, then this is going to be the integral of gamma prime T dt, okay? Right. So therefore, it's reasonable to define the length of the curve by this integral, okay? So we get this formula. And that's how do we find the length. Okay, and we see that this is another important factor is really independent of the length of the curve should be independent of the parameterization of this curve. In other words, the length of the orbit should be independent of the moving object, how fast it's moving, right? There's two cars moving around the road, right? And you get the position vector for each of them. And you use each of the position vector, you find evaluate this integral then you should end up with the same length. Otherwise, this is not the right definition. Okay, so here's the important fact. So if gamma tilde, t tilde, right, is another, we call the parametrization of C, okay, C's orbit, right? Then we have this identity in calculus. This is called the substitution, in other words. Okay, A tilde, B tilde, gamma tilde prime, C tilde, D tilde. Okay. So no difference. If we integrate, no difference. But the derivative could be different. Okay, the interval could be different. A to B, A tilde to B tilde, that's different. And this is called a substitution. From here to here, in calculus, called a substitution. Remember when we change the variable, right? And the integral will change. And this, you end up with same value, even you change the variable for the integral. You should get the same value eventually at the end. So this procedure just, in other words, this is just substitution calculus. We already know that. Okay, and so we're not going to spend too much time on this important fact. We just use that, accept the fact. We cannot verify everything, you know, what's already written in the textbook, but we use that to find the length of the curve. Let me say a few words about it. What's the difference between science and engineering? If you're a science major student, you should know more about why this formula is correct. Okay? All right. So we usually always ask yourself why is this true? And as in engineering, we always say how to use the formula to solve the problem. Is there any tricks, you know, we have to learn? Okay. But the majority of the students in this class are from engineering, not from science. Very few students choose math major. Well, let's take a look at the example here. So the curve C is described by this parametrization. Cosine 3t, sine 3t, and 4t. Okay, if you want to describe this curve, this is a helix. Right, and t is between 0 and 2 pi. And I think rotate how many times? 3 times, I think. 1, 2, 3. I think something like that. I want to find the length of this. Right? Find the length. Now, the parametrization is already given. So I will give you another parametrization later. But this is one of the parametrization. Okay? So the orbit in the space is right? Right? So use this parametrization, then you can use the integral, right, to find the length. So if you want to solve this problem, the first thing you have to write on the formula, okay? So the length of C is going to be the integral from 0 to 2 pi gamma prime t and the dt. Right? You write on this formula first. That helps you to get maximal partial credits. Okay. Yeah, you know, when I check my son's homework, he always put just answers there, and I cannot read it. And I keep telling him, you know, you have to build a good habit. You show the details, right on the formula, if you want to get more partial credits in college. Even I can show him the, you know, a quiz. I say, you know, I say, look at this. You know, it's harder for me to give partial credits because I don't understand what formula he's using, but the answer is wrong. You know, that's it. It's not easy to change the habit because it's school that don't talk about that. All right, so you write down the formula. So you know it's very clear mind that you're going to use this formula to find the derivative. The next part is just how to do the computation carefully and evaluate the integral. Sometimes you're not able to evaluate. Okay. So the derivative of this function is going to be negative sine 3t 3. Okay, and then 3 cosine 3t and 4. Okay. Then I needed to find the length. Right, find the length. So I don't want to skip any steps. Now after I put everything into the formula for the length of the vector, then I can work on sketch paper, just save the time, you know. Then I find out the first term is 3 square, second term is 4 square, the answer is 5. Right? It's constant. All right, so now you put back into the formula from 0 to 2 pi and the 5 dt. 5 is constant, so it's just 5 times 2 pi, it's 10 pi. So 10 pi is the answer, is the length of the curve. All right. You can reparameterize another parameterization. Yeah, you can normalize. You can let gamma tilde t tilde, to be 3 cosine 3 t tilde and 5. For example, sine 3 tilde and 5 and 4 tilde over 5. Okay. And then just because that t tilde is between 0 and I think it's going to be 10 pi. Right? Yeah, when t tilde is 10 pi, I got 5 times 5 theta, yeah, it's going to 2 pi, yeah. Okay, so this is if you draw the orbit of this moving object, you get the same orbit. Okay, but the difference is this is going to be here's 5 over 3 negative sine 3 tilde 5 and 3 over 5 cosine 3 5 t tilde and 4 over 5. Okay, so if you want to find the length, it's going to be equal to 1. It's going to be 1. The reason is it's going to be 3 over 5 squared plus 4 over 5 squared. It's going to be 1. So it's just a constant speed, in other words. Unit speed, yeah. Constant is also, original parameterization is also constant speed. So, oops. So, so the length, according using this parameterization, it's from 0 to 10 pi. All right, so it's since this is just 1, so you still get 10 pi, okay? Now the relationship between this parameterization is that t equals, yeah, I think t tilde equals 5t. That's the relationship between those two parameters. So when t is between 0 and 2 pi, t tilde is between 0 and 10 pi. Okay, so you just replace t by t tilde over 5, and you get a new parameterization. In other words, this is equal to gamma t tilde over 5. You know, right? That's the relationship between those two. Okay, just replace t by t tilde over 5. All right. Now, as you can see that t tilde is a very nice parameter. The tangent vector has unit length. My question is, can we always, yeah, given, here's a question, given given gamma t, okay, can we find the and we find a new parameterization, S equals S of t, such that, okay, such that for this new one, okay, this is supposed to be, how can I, yeah, so it's related to gamma t, okay? Has the following property. So this one is a new parameter, right? So I can find the inverse. T is going to be, yeah, if I use better use another function here, f. So that'll be inverse of f, okay? So it's gamma alpha, okay? Such that gamma prime s, I'm not going to use s2 then. I don't know why it's 2 now. This s. So this one is as unit length. Okay. Yeah. I think it's possible. First of all, we have to figure out how does S depend on T. Okay, assuming it's possible, then we can get equation. Right, how can I do that? So I differentiate because S is a put, you know, you can also express like that. Gamma T equals is going to be, yeah, let's see. So let's find out the relationship between S and T, these two parameters. I want to reparameter that, right? I try to find f of t. So what is f of t? So that if I replace t by s, I cannot just replace t by s directly. T is going to be a function of s, so just replace that. Then I get the vector value function in s. And then it must have this property. What I'm going to do, I differentiate both sides, right, with respect to t. So the right-hand side, s is a function of t. So that's why I have this, and this is gamma parameter, right? Okay, then I take the norm. I find out, since this is going to be 1, right? So I find that ds dt must be equal to the derivative. All right, so that s cannot be arbitrary. If we find that, s must be, you integrate on both sides, right? You know, our t is, suppose, yeah, t is between a and b, okay? So starting from here. So this is a curve that t equals a, that t equals b, and this is a parameterization gamma. That's origin, right? So I integrate on t, and so ds dt, I use a yeah, I use I'm going to use a tau here. Yeah, d tau integral from a to t. Right. So the left-hand side is s t minus f of a. The right-hand side is this. Okay, what does that mean? That means this is the length. The length of the curve C from the starting point gamma A to the point gamma T. So this is a portion of S. Okay. So if you so you already find the yeah, if S is f of t, right? So that is should be f. That should be f. Okay, that should be f. All right, So you get a function of f. The function is completely determined. Okay. It depends on the initial value. So f of t is going to be f of a plus. So if such parameterization, new parameter exists, then this f is uniquely determined, which just gives a length from a to t equals a to equal t equals t, right? So look at the picture here. And so if you're able to find the length of the curve, you can get the parameterization, new parameter. So this is the S, okay? Then you can solve for t in terms of S. Then you can get, then you can get, okay? Then you have a gamma t is replace gamma F. And this is going to be denoted by another notation, okay? That's how to use this procedures, okay? But that depends on whether you are able to evaluate this integral. So let's take a look at some, the example we did. I think we did so let's go back to the example, okay? Gamma t equals cosine, and a little bit more general, a t sine a t and bt, okay? If you want to, I think I'm going to move a to the all sides because I want to make sure this is on the cylinder with radius r and radius a. So it's t, a, a. Yeah. Okay. I think a complete circle t from 0 to 2 pi, you give it a circle like that. I think it's coming to here from this, this is on the cylinder, right? So we just want to find, this is a cylinder, right? With the radius equal to a. Okay, so this is a curve. I want to find a new parameterization. Right. Find the parameter s. So I can the right now the tangent vector is not going to be has constant is not going has a unit length. So if you differentiate, right? So you will get right. This is the formula. So think about this is how do we do, right? Step one, I have find the length of this. Right. Okay. All right. So we get a square plus b square, right? Yeah. So now I'm going to find the function this is it's going to be the integral, right? And that's, we don't need to know exact value of this. It's from 0 to t, d tau. So I got, so finally, it's a constant, so it's easy to do. Fine. All right, so my S is f of t, and this is going to be f of 0, some constant, right? So it's not the initial value doesn't matter, okay? You can call it S naught, okay? So we have a new parameter. From this new parameter, I can also find the S. So it's going to be S minus L. Okay, that's a relationship. All right, so now gamma t, remember it's A cosine t, B sine, A sine t, and BT are replaced by S. All right. Yeah. So this one now is dependent function for S. So I use gamma tilde. It's a new function with a new parameter. All right. So what is the range for S? If you look at the picture here, S minus naught is going to be greater than equal to 0, less than equal to square root A squared plus B squared, and 2 pi. So that is the range. That's a, yeah. This is a, the value for S. Okay. So S is between 0 and S minus S. All right. So anyway, we got the new parameterization for the same curve, but now it's in S range. And you can check that. We can verify that gamma prime S, but if we differentiate, it's always going to be 1. It has a unit speed. It has unit speed. Okay, so why we're interested in the new the parameterization with the unit speed? Because we can use that to describe the curvatures of the curve. Okay. Yeah, let's take a look at, right now I'm going to assume that, okay. So given a curve, I'm going to use S, okay? Assume that gamma prime S is going to be 1. Right? And here S equal S naught, right? The starting point, going that way. So actually, S minus S naught is going to be, in this case, S minus S naught is going to be the length of the curve C from gamma S naught to gamma S. Okay? I should say that. Okay. Since it's a unit vector, so I'm going to let T to be gamma prime T. I have to use it. Yeah, I'm going to use this. Okay. I will remember t times t is going to be 1, right? So I did it last time, I differentiate both sides with respect to s. If I differentiate with respect to s by the product rule, it's going to be 0, right? The right-hand side, the derivative 1 is 0. The left-hand side, you get 2 terms. Right. So since this can be commuted, the dot product is commutative. That's why those 2 terms combine into 1. That's going to be 0. So that implies it's perpendicular to the tangent vector. Okay? So think about that, right? So this is a picture. This is a tangent vector. And another vector may be shorter. That is a derivative. And based on the experiment, I found out, first of all, this is a direction where the curve is curved. Okay, it's bending. Second, the length of this vector t prime. Okay, if it's getting longer and it's bending more. Okay, if it's smaller, the length, it's more flat. Okay, this curve. So that really measures how, I call it curvature, right, of this curve. So here's the definition. So we define this to be the length of this derivative is called the curvature. So when you do research up to this point, right, you understand this is a new quantity, the length, but does not tell you the direction. If it's long, yes? Left-hand side? That's just as this. Yeah, it doesn't matter. I just let k to be the length of this derivative. The length of this derivative. Okay, derivative uses 2 different notations, t prime, and so this is called the curvature of the c at the point at that point. All right. So when you do some scientific experiment, sometimes you observe that this is the length of this, for example, in this case, the length of the derivative fact really tells you how curved, how sharp this curve, it's bending. And you can check the circles. Okay, so you can name it, called curvature. Okay, don't just, you can look at the textbook, look at scientific papers, there's nothing there, and then you should be happy about that. Then you're the first one to introduce this quantity. Right? All right, so now you have a curvature. So we have to make a further assumption. Assume that this curvature, this is not going to be 0. Okay, in that case, I can normalize it. Okay, I can normalize this is a TS, that's a T prime. When I normalize it, I get this NS. It's a unit vector, okay? That's a T prime S. T prime S may be short, maybe long. And we see that NS is going to be 1. NS is perpendicular to TS. Okay, not too bad. Once it's in 3-dimensional space. Once you have a TA, you have an N. What happens? You can define another one, right? You can define BS to be TS, the cross product in 3-dimensional space. It's in high-dimensional space now, right? in three-dimensional. You can do it. And since we live in three-dimensional space, we always think of things in three-dimensional space. But it's possible, you know, four-dimensional, five-dimensional, six-dimensional. That will be out of imagination in most of the cases. All right. Okay, so this is so then you have what? You have a T, you have an N, then you have another one called the B. They're perpendicular to each other, right? So in the space now you have a frame. We call it frame, okay? At every point, there's a three, okay? And of course, this BS has unit length, and BS is perpendicular to TS, DS is perpendicular to NS. Right, that's another. So you have three vectors now. What's the meaning of this three vectors? I think when you have a curve, the curve, it's in general, it's not a plane curve. So when you rotate, not only this is it curved in that direction, but also the curve is leaving a plane. So that direction B really tells you that, yeah, it tells you the direction which the curve is leaving the plane. You know, not if the curve is not a plane curve, then how bad it is, right? So it's somewhere, some direction, not only curved, but also leaving the, so helix is easy to observe it. The helix is, the curve is curved in that direction. At the same time, it's going up in that direction, leaving the plane, okay? So this is a helix, okay? That's two directions. This is a B, that's N, this is tangent vector T, okay? So the direction B is also important, that in which the curve is leaving any given plane. Right? The plane is spanned by T and N. Right. Okay, so what do we want to do today? We want to we want to compute the curvature, even we don't have the nice parameterization. So sometimes it's not easy to find the parameterization with a unit length. You know, the tangent vector is unit length. It's not easy. So how to find curvature at a given point? So there's a question, okay? Given gamma t, right? My question is how to find the curvature. Yeah. How to find the curvature at gamma t, right? Without using the special parameter S, right? Without finding S. Right. You know, right? Because in some cases you're not able to even compute evaluate integral. You know that integral most of the time you are not able to evaluate integral. Right? If I randomly give an example, you cannot evaluate the integral. So we have to solve the problem step by step. Okay. I know. Yeah. So I know S is related to gamma t by this formula. Right? So theoretically, you have this relationship. Right? Right. How they're related, right? S, you can replace S by this, you can get gamma t. So that's a relationship. Okay. So I differentiate with respect to t. So this is identity. So this, in other words, this is going to be so you have this identity. Okay. All right. So what is our t? We needed to find a t here. T now is going to be gamma. Is going to be gamma prime t. It's a function of t right now. You have to normalize it. So t depends on t and capital T depends on t and or depends on s. So this is our identity. Right? And this can be function of t, this can be function of s. So it's easy to find the t. Now, to find right, uh, so t is given by this. So gamma prime t is going to be capital. If this is a function of t, then capital T d ds dt, right? You can write to this form, because ds dt is gamma, is the length of the gamma. So I'm going to differentiate twice. I'm going to differentiate twice. So this will be, it's a product rule. Okay. So that is a derivative of dt. I'm going to change change it to ds. That'll be ds dt, and then ds dt here. All right. Then right. So you can view this as a function of, I'm going to use the same t here, okay? View it as a function of ts or a function of, if I really want to tell the difference, maybe I needed to, if I want to use a primary, sometimes we use a t tilde, okay? So this change it to the t tilde, yeah, let's use this one, right? It's the same, the parameter, right? So the parameter is different. Yeah, that's why the function is different. Okay. Yeah. So this is a unit. This is a unit vector, right? This is also going to be gamma prime tilde. Yes. Okay. All right. So now what I'm going to do, I do the cross product. Okay. I do the cross product, and this time that is going to be this time this. So it's t. Okay. It's going to be t times t times t tilde. Okay. ds and the ds dt cube, and the t times this two will be canceled out. So you only have these two terms. Okay. And if we use right now, if we view it as a function of s, that'd be s tilde, right? So this can be viewed as s tilde ds dt. Okay. If it's viewed as a function of s, then I use a t tilde because the formula is different. Anyway, you have this identity. Then remember, this term is tilde, so it's curvature times n, right? Curvature times n and ds dt. Yeah, that's how do we define the curvature and the normal vector, right? So that will be curvature times v tilde. Yeah, I'm going to use a, or use a tilde here whenever the parameter is s. All right, so we get this identity. We not only find the curvature, we also find the vector b. Okay. And remember, yeah, this n tilde s is going to be and t tilde prime s, the normalization of that, which is going to be, this is going to be k, okay? And the k is going to be the length of that, okay? B tilde is the cross product. So we have this following identity. All right, so I not if I take a norm on both sides, okay, I will get so from here I solve for k because that is gonna be 1. So I get this is going to be d gamma prime t and cube. Okay, so this is a formula, curvature formula, right? And you can also since you already get a k, right? So you can also use that to find the bs. I think that should be k, and I think that. Okay. So in other words, this is going to be gamma prime t. All right. So that is a formula for that normal vector. All right. So in order to find the curvature for an arbitrary parameterization, you just need to find the derivative and it's the second derivative and do the cross product and then using this formula to find the curvature. Okay. All right. So here's the example. Yeah, here's the example. Gamma t equals 1, t and t squared. Okay, I want to understand the curvature. So if you look at the picture, I think this is a parabola in the plane perpendicular parallel to the y axis, z axis. Okay. So I want to find the curvature hey, at point gamma t. Now, if possible, we also want to find out find the t and b at the point gamma t. Okay. The unit tangent vector t, and that is a vector n. Then the one perpendicular to that, that's a b, right? You don't need to find, but those are defined using the arc length we call S parameter. But it's difficult to find this. Right? Look at this. Look at the gamma parameter t. That's going to be 0, 1, 2, t. And if you really want to evaluate this to find the S, it's very difficult. Okay, so this is going to be integral 1 plus 2t squared dt, and even you can evaluate the integral. That's a very complicated formula relationship. Okay, I don't want to do that. All I needed to do is just give me an arbitrary point. Even the parameter is still t. I want to tell you how curved this is curved at that particular point. So I find that the second derivative, right? Then the cross product. Okay, if you do this, then be very quick. Cross product is going to be I, J, K. I think I'm going to have a 0, 1, 2, t. 0, 0, 2. Right. All right, so it's going to be 2i. I think it's going to be 0. Another one is going to be also 0. Okay, so it's going to be 2, 0, 1, 0. It's very interesting. So it's constant. It's constant vector. That's okay. So the curvature, remember the curvature is going to be gamma prime t. So that is curvature. So this is going to be the square root of 2 square plus 0 square plus 0 square. And the original curve is going to be 0 square plus the derivative, 2 square. I'm going to get, and that tells you the curvature goes to 0. This curvature is never be bigger. See, k is always less than or equal to 2. K approaches 0 as t approaches infinity. Yes? Q. There's no Q here. Where's the Q?
Q.
Oh.
Gamma prime t.
Yeah,
Q.
you're right. You're right. I'm missing. Yeah. All right. So anyway, this is going to be so when the parabola is getting far away, it is going to be it is going to be it's going to be more flat. Curvature is going to be zero. So at the point gamma t, right? Remember, I already defined the curvature, which is gamma prime t. I think that's going to be 0, right? 0, 1, 2 t. Yeah, 0, 1, 2 t. 0, 1, 2 t, and the square root of 1 plus 4t squared. Okay, I also find it's difficult to find, but I find a b. Using that, you can find n. Okay, the b is going to be the unit vector of this. So it's just 1, 0, 0. So B is simple, just constant. So once you find the B, then you can find the N. I think N is B times T. Look at this picture, right? N is B times T. So N is a B times cross product. Okay, so using that will be much easier to find the N. Okay, that's how do we do the calculation. Okay.